In this section, we will look at the same problem of a drag on a sphere, but this time with scaling analysis. Okay, so here the problem is still exactly the same, and we want to find a non-dimensional scaling law for the drag. So here we'll still reason with the dimension, but on top of that we'll add a little bit of our knowledge of the physical system. And we'll see that we can infer a little bit more than just what we had in dimensional analysis. So let's start by, we'll assume that we know a little bit about fluids already, and so you have some idea about the Reynolds number and some idea that perhaps things are a little bit different depending on the scale of the velocity, whether the sphere is moving really fast or whether it's moving really slow. So let's assume first that the sphere is moving at a large velocity. Alright, so in this case we will look at the drag. So we want to know what is a scaling for the drag. And when I say scaling, then it's not a non-dimensional scaling. It's really just what is a scaling for this quantity. How does this quantity look like? Now, with some knowledge of fluids which you have from your bachelor's, you know that, what is that? That the drag will essentially be caused by a static pressure. So as the fluid, as the ball is advancing, the flow here is stopped, so it will scale with the static pressure times the surface of the sphere, so something which scales with the surface of the sphere. We don't really care too much about the constant, but the surface of the scale of this the sphere will scale with a squared, our length scale squared. Now, what is a scale for the static pressure? The static pressure scale with rho u. So in the end we have a scaling for the drag, which is rho times u squared times a squared. So our static pressure times our surface. That is our scaling. And then if we use on top of that what we know from Buckingham pi theorem, if we are at large velocity and we assume the effect of viscosity are negligible, well then in that case we have really only four relevant physical parameters: a, u, the density, and the drag. So we have m equals 4. We have n, which are the units, equals to 3, so p, which is m minus n, is equal to 1, and therefore we know that this non-dimensional number, that the one non-dimensional number is a constant, and the non-dimensional number that comes out of this scaling analysis here is d divided by rho u squared a squared, which is a drag coefficient. And so we know that this is going to be a constant. Okay, now let's go to the other extreme. Let's assume that we have a very small velocity, and in that case we know that viscosity is going to dominate. Now here we have to again find, and let me tell you that this will happen only at extremely small velocity, or when not just small velocity but very small spheres as well. But let's assume that the effect of viscosity is the one that really dominates. Then we have to find a scaling for a drag, and in this case our drag is going to scale with a viscous stress. Right, so here we had a pressure. Pressure has the same units as stresses, so pascals. And what is, so the drag will scale like a viscous stress and the viscous stress is applied on the surface of the sphere, so the viscous stress times a scale for the surface, which is still a squared. Now, what is a scaling for the viscous stress? Right. We know, you know from bachelor, in your bachelor, is that a viscous stress is the viscosity times a shear rate. Now, what will be the scale for this? So here, this scales with mu, and the gradient, so the partial derivative of u respect to a length scale, so this is your shear, will be a u that needs to be a velocity, so velocity, your only velocity scale is u, divided by a length scale, your only length scale is a, so this will scale with mu, u divided by a. And therefore, I have that my drag coefficient scale with mu, u divided by a times a squared, so times a. Okay, now, so this is my scaling law, my scaling for the drag, when, my scaling for the drag when viscosity dominates, right? Now, I want to rewrite it in terms of the non-dimensional parameter which I introduced here, which is the drag coefficient, and therefore I divide both sides by rho u squared divided by a squared, both sides divided by rho u squared a squared. So this yields, this here is my drag coefficient, and that here you will recognize u cancels, my a cancel is 1 over the Reynolds number. So in summary, from scaling analysis, we find that for large velocity, when viscosity is negligible, which is the same as to say when the Reynolds number is large, so it's much larger than 1, in that case, we find that our drag coefficient, we expect our drag coefficient to be a constant. So we expect our drag coefficient to be a constant. And on the other hand, when the effect of viscosity are dominant, so when the Reynolds number is really small, from scaling analysis, we expect the drag coefficient to be scaling with 1 over the Reynolds number, and that is simply from a scaling analysis, right? So is that verified experimentally? Now the answer is yes, and what you can see here is that the scaling analysis gives us the form of what was of the function which we wrote from dimensional analysis. So from dimensional analysis, we know that CD should be a function of the Reynolds number, but we don't know what this function looks like. But from scaling analysis, here we see that we expect the function, the drag coefficient, to depend on 1 over the Reynolds number for small Reynolds number, and to be constant for large Reynolds number. And those scaling laws oftentimes are best visualized on log-log plots. So just briefly, what is a log-log plot? In this case, for instance, we know that our drag coefficient is going to be a function of the Reynolds number, right? But really, from our scaling analysis, what we found is that our drag coefficient was a power law of our Reynolds number, and in that case alpha was equal to 0 for large Reynolds number because it was a constant, and alpha is equal to -1 for small Reynolds number. Now these kinds of power laws experimentally are best seen in a log-log plot. And what is a log-log plot? Is a plot where you don't plot the drag coefficient as a function of the Reynolds number, but you plot the log of the drag coefficient as a function of the log of the Reynolds number. Now, why do you do that? Let's compute the log of the drag coefficient. So the log of the drag coefficient is equal to the log of, in that case, the Reynolds number to the power alpha, right? And that's a property of the log. This exponent here you can put as a multiplication factor here. So that for power law, you have that the log of CD is equal to alpha, the log of the Reynolds number. And if you're plotting in log-log plots, that means that you're plotting log of CD, so this is your y, as a function of the log of the Reynolds number, this is your x. And then your power law here looks like y equals alpha x. So a power law in a log-log plot simply looks like a straight line. And the straight line has a slope which is equal to the exponent. So what we have from my scaling analysis is that we expect, if we're plotting in log-log, so in the x-axis I'm plotting the log, I have the log of the Reynolds number, and in the y-axis I have the log of the drag coefficient. So at high Reynolds number, when the effect of viscosity are negligible, well then we expect, for large Reynolds number, alpha is equals to 0, right? So we expect the log of CD to be equal to a constant. So here, this is equal to a constant. The slope of a line is 0. However, at low Reynolds number, when the effect of viscosity are dominant, then we expect the log of the drag coefficient to scale on to, so then the slope here is going to be -1, because the exponent is -1 in our power law. So we'll have a straight line, but with a slope of -1. So we expect our drag, that if we measured the drag and we change the velocity, for instance, and then plotted the log of the drag coefficient as a function of the drag of Reynolds number, we expect from scaling analysis that we would get something like that. Now, what do you get when you actually do the experiment? You get the following. So here is an experimental curve, and you see that you do have, for large Reynolds number, so here the Reynolds number is large, you have something which is roughly constant here. And when the Reynolds number is really small, well, you have something which looks somewhat straight here. And now, what is a slope -1? You have to see here, this is 1 decade, and this is here 1 decade. So a slope -1 is this here. So you clearly see that here you have a -1 slope. Right? Now, so what we expect from scaling analysis is really relevant, and you see that our experiments confirm that. Now, what our scaling analysis doesn't predict is this here, right? And that in a way makes sense, because this here has to do with the transition to turbulence, and we didn't take any of that into account in our scaling analysis.